model. That's good. Okay, let me to introduce you, Max. By the way, I don't know if my pronunciation is correct, but your name is Max Yarenchuk. Okay.
Yes.
Thank you. And so let me to introduce Dr. Max Yarenchuk. He is a research scientist at the Naval Research Laboratory in Stennis Space Center, USA. His research interests are in computational methods and their applications to data assimilation using both variational and ensemble methods. He has an extensive experience in the development of 4D variational assimilation systems in oceanography, including general circulation, sea ice, and surface wave models of various complexity. Dr. Max has been invited to serve as an expert for multiple National Science Foundation in USA panels in computational mathematics and NASA oceanography programs. He is an author of more than 60 publications related to the development of variational data assimilation methods in oceanography and their applications. Please, thank you very much for accepted our invitation, and please go ahead with your presentation, Dr. Max.
Okay, thank you, Harold. This is the last talk of today, and it's called the Adjoint-free approach for 4D variational assimilation, but in general it will kind of give you a little more general perspective on the application of the methods of data assimilation, with more emphasis on the role of ensembles in data assimilation. In the previous talk, Dr. Lawless gave a very nice basic presentation of these connections between the variational methods and some stuff regarding the ensembles. And what I would say that this presentation is go a little more beyond the application of the adjoint-free methods to variational assimilation. But for example, it will just touch some questions regarding the extraction of the tangent linear models using the structure of the tangent linear models using the ensembles and other applications like sensitivities and so on and so on. So the outline is just maybe first of all I will talk about why the adjoint-free. So what are the problems with the derivation of the adjoint and performance of the adjoint and the tangent linear models in application to data assimilation. And so I will show just the role of the ensemble techniques in basically these techniques are a kind of you can consider them as a brute force methods to computing the sensitivities of the and cost functions and basically the data assimilation sensitivities to the variations of the control variables. And I will talk about using the ensemble methods without any adjoint models to estimate the and approximate the gradients of the cost functions, then also on the retrievals of the tangent linear models and the adjoints from using the ensemble, solely the ensemble information. This is a really very fastly developing branch of computational science right now in the data assimilation. And finally, I will talk about the application of the one of the adjoint-free methods which we have been developing over here and applied to models of various complexity, and so-called the adjoint-free method of data assimilation. So first of all, I will just talk about the origins of the development of the variational and ensemble methods are closely related to the progress and the development of the computer technology. This plot shows the logarithm of the speed of computations for the 500 for the fastest 500 numerical for the fast 100 computers in the world as a function of time. So as we see, the variational methods basically they emerged around the 1980 when the computer memory was expanded to the state when it was capable to hold in memory the model states with a reasonable resolution, so that the models could operate with the states holding them in the memory. And then the variational methods were proposed, which can compute the gradients with respect to parameters using the so-called adjoint models and the tangent linear models, as in the previous talk, as mentioned in the previous talk. But after that, the computers came. This happened around the end of the previous millennium. The computer technology came to the limit of a single CPU computational speed, which is around 3 gigahertz. Some maybe fancy stuff might be like 40 gigahertz, and this is a limit dictated by the physical principles, fundamental principles like the speed of light and some quantum physics constraints based on the difficulties in cooling the processors at this, in cooling very small processors at this very high frequencies. So in that sense, the development of computer technology stalled. I mean, in terms of the speed of single CPU, but at the same time, a trend of massive parallelization started, which is shown here by this yellow rectangle. And so this massive parallelization was kind of going far. As you see, there is a kind of inclination point on this, on the graph of the speed of computer performance with time. And this, even by now, we are approaching the speed of 1 exaflop for the most advanced systems. And this is the major trend in the computer technologies in the most advanced computational centers, which also, of course, employ various algorithms for data assimilation. And regarding this trend, there are more and more emphasis is made to the application of the ensemble methods. And while, in my opinion, the adjoint methods based on the direct differentiation of the code and the derivation of the adjoint methods by the adjoint compilers are going a bit more outdated. Maybe I'm wrong, but still more and more efforts are made to derive the model sensitivities and the gradients and all the related quantities using the so-called, so to say, brute force by just perturbing the states of the atmosphere and the ocean and looking at the at the output and then deriving the sensitivity maps from this computations. So, and there are also some problems with the adjoint models. The first problem is the so-called dynamical causality bottleneck. As you remember from the previous talk, first you have to run the forward model, then to run the adjoint model to compute the sensitivity or the gradient of the cost function with respect to the control variables. And you cannot bypass this sequence just running for one more forward in time and the adjoint model backward in time. And for example, a good example is just the performance of the global ocean model run in the Naval Research Laboratory at 1/25th degree of resolution. This is the dependence of the wall time in minutes per integration day. And this is the number of processors used. So at this resolution, there is a kind of stagnation. The linear trend, the whole time decays most linearly with the increase of the number of CPUs, but at some point, basically at approximately 30,000 processors, you start to lose the efficiency of the parallelization, because the tiles become so small that the time of computing interconnections between the tiles becomes comparable with the computation of the advancing of the model state within the tile. And this is also kind of fundamental limitation of applying the adjoint models to adjoint codes to such a big models. The second issue is just the development and maintenance cost of the adjoint and the tangent linear models. Because, again, from the previous talk, I heard that it takes, and basically at our lab, it takes years to develop the tangent linear and the adjoint code for a sophisticated model, say, of the ocean circulation. And besides, as the model develops itself with time, the tangent linear and the adjoint codes should be also updated. This requires a lot of efforts as well. And the final thing is that the models per se are not basically differentiable, because there are a lot of physical processes, for example, like in atmosphere, the rain is, or in ocean, the deep convection. These processes are kind of abrupt. The respective operators cannot be differentiated just using using the standard mathematical analysis. So in any case, the tangent linear and the adjoint model of a general circulation model are not exact. They are still a kind of approximation to the exact sensitivity map. And the final thing is that these linearized models are unstable. So, for example, if you have a state which behaves, which shows some nonlinear instabilities, the corresponding linearized model will have the corresponding operator of the linearized model will have eigenvalues lying outside the unit circle, and some modes will be exponentially growing. And I will show later what is the effect of these modes on the estimation of the cost function gradient. So, and for these reasons, the approach which uses the ensembles becomes to estimate the model sensitivities becomes more and more attractive. So again, from the viewpoint of variational technique, what is say the standard variational approach? Using the adjoint and the tangent linear model. The adjoint model provides you with a so-called steepest descent. So if this is a kind of idealistic diagram showing the cost function levels of the cost function map in the idealized two-dimensional case. So if this point, this yellow circle is first guess solution, then the gradient shows you the direction of the steepest descent, and you go find the minimum along this direction and then converge to the optimal point in 2 iterations, because this is a kind of simplified 2D case, but just to have an idea how it works. On the other hand, if you say, for example, have 2 CPUs or maybe more, like 3 CPUs, and can blindly search in several directions, shown here by green lines, you see that you can converge in this particular case to the minimum in just 1 iteration, because you can use these 2 directions and optimize the cost function in 2-dimensional space, not consecutively in 1-dimensional space, like in the adjoint adjoint method. And of course, if you generalize this pattern to, say, the space of 1 million dimensions, it becomes a little bit more tricky and not as simple to use the adjoint-free techniques to study the sensitivity of the models to the free parameters. But still, if you do not use if you do not search like in blindly in various directions, but you have some prior information on the structure of the model or of the cost function, you can make a smart choice so that these directions would be located within, say, a cone of the steepest descent direction, and you can perform, you can do minimization even faster than the variational method, assuming that you have enough CPUs at your disposal. And another thing, again, is just which should be considered, that the linearized models and the adjoints, which are used in standard variational methods, they require several times more computational time, more CPU time compared to the nonlinear model. This comes from the necessity to keep the background state while integrating the adjoint and the tangent linear model, either keep it in memory or recompute it in the process of integration. So the application of the adjoint and tangent linear models could be computationally pretty expensive. So the first thing I will talk about is the so-called gradient approximation using the ensembles. It has more in common, many more in common with the previous talk of Professor Lawless, but still I will just briefly show you the major principles which are used in this approximation of the gradient using the ensembles. So the tangent linear and adjoint models are not really used. Say the cost function, again written in terms of the increments, so the differences between the current trajectory and the background trajectory can be written in this way. So, and let's forget for a while that this M is a linearized operator. It can also be a nonlinear operator, same as just the observational operator acting on this unknown increment. So again, the standard way, again from the previous talk, to use the so-called square root preconditioning is to introduce another variable like blue x. It was z in the previous talk, and then the inverse transformation, which was u, is just the square root of the background error covariance. So as you may understand, so you move this inverse square root over here, so the original perturbation of the control variable will be just the product of the square root of the background covariance by x. Then, so if we plug this preconditioning over here, we get this equation, and then the trick is again just we approximate. If we have an ensemble in our disposal, then we approximate the background error covariance B as the product of the ensemble perturbations. These are just each perturbation can be computed by simply taking the difference between the ensemble member and the mean, but this will provide a so-called low rank background error covariance estimate. So in that sense, all the search for the minimum of in this cost function will be performed in the low dimensional space, which has the dimension n, and n here is the number of ensemble perturbations. So we are kind of limited to a specific subspace of the entire state space in the search of our minimum, which is not good. And in that respect, let's continue further. Just if we still do not talk about the localization, but still remain in this subspace spanned by the number of ensemble members, we see, for example, that action of this matrix can be just computed as the integration of the ensemble of model integrations applied to each ensemble member. So it will be the matrix of this size. So the n is the number of rows, and n again is the number of ensemble members. While x in this case, x blue in this case would be interpreted as a number of coefficients. So basically the number of modes which constitute the ensemble. So it would be just a very low dimensional vector of unknowns, since we are looking for the optimal states since in the space of this ensemble spanned by the ensemble trajectories. So, and then the gradient approximation would be very simple, and the number of the computational efforts to compute the gradient again will be not as big, because you can this matrix, which has to be transposed, still has a relatively number of low number of elements. Just it would be the size. It will have the n capital number of rows, which is just 10 to the 8th, and n is the number of ensemble members, is just around 100. So it's doable in using the modern computers. So the gradient in this low dimensional space is more or less would be easily computed. But on the other hand, of course, as I said, this gradient and the approximation of the gradient will be still live in this low dimensional subspace spanned by the ensemble members. On the other hand, since it's spanned by the nonlinear trajectories of the model, it would not be it would not have instabilities, because all the nonlinear trajectories still, if they, for example, conserve energy, they will not just go exponentially big in the process of integration. So the good thing that you will never observe tangent linear instabilities which emerge in the tangent linear adjoint models, and limit the integration times of the tangent linear adjoint models to pretty small time intervals, especially in the regions of nonlinear instabilities. But the disadvantage is that, as I said, it's constrained to the subspace spanned by the ensemble members. So what can be done with that? So the standard approach is using the localization, so-called localization of B, also covered in the first lecture today by Professor Miyoshi. And so the localization matrix is usually depends on the distance between the state variables, either in the ocean and the atmosphere, and it has also some disadvantages. So, for example, if the half width of this localization matrix is pretty small, but still you may, since you do not distinguish between the different fields within the bundle of trajectories, since you do not distinguish, for example, if you are trying to estimate the correlation between, say, velocity and temperature in 2 points which are not far from each other, then localization matrix does not help to reduce the noise, because velocity and temperature may have correlation which is not large, while the sampling error would be compatible with these correlations, and the localization matrix would not help, and the result of assimilation may not be very good. And one thing which can be done in that case is that you can compute the localization matrix by say, computing the major modes of the trajectory at the interval of interest, I'll say, at the so-called assimilation window. You can compute the major EOFs of the snapshots of the model trajectory and decompose them. So, and the number of snapshots and truncation can be done at maybe 100 modes. And in this case, these modes will capture the major variability of the error fields on one side, and on the other side, they will kind of reduce this problem with localization, which just based solely on the distance between the points, because these modes will then take into account the intrinsic correlations of the model trajectories and say the correlations between velocity and say temperature, which in the points which are not far from each other would be just not as large as in the case of the distance related localization metrics. So in that case, if you use the localization like that, then the perturbation matrix X prime will be just the tensor product of the original perturbations and the square root of this localization matrix. So it will increase in rank, of course, because then now the matrix of the perturbations in the observational space will have this rank, where m is the number of observations and k is the product of the number of truncation number of the localization matrix and the number of ensemble members, but still it's manageable. And so the dimension of the optimization subspace is, first of all, it's expanded compared to just the raw ensemble, but of course it's done by the expense of the larger memory requirement, because you have to involve, and in this case, approximately 10,000 modes to compute a reasonable approximation to the gradient. But this technique was first introduced around 10 years ago by Liu et al. And it's called the so-called 4D var. So it's completely free from the computation of the derivation of the ensemble of the tangent linear and adjoint models, and appears to be working more reasonably well. So basically, there is also a very big question regarding how do you generate the ensemble. So there is a huge literature on that, and these methods a lot of methods exist, and they, for example, you can do perturbations by using the leading Lyapunov exponents, like in the paper of Trivisian of 2010. Then the iterative subspace minimization, like derivative-free optimization by Gartner et al., trust region framework, and a lot of other methods. But these methods still, of course, are tailored for. There is no recipe which is applicable to all situations. So these methods are tailored for certain problems. Some of them can be done with not really big, large dimensional environments like we use in operational forecasting, and some of them work in many more dimensions, but there is a lot of literature on that, and it's reasonable just to have a look if you have some problems, specific problems in applications maybe going beyond the environmental forecasting. So, but another interesting thing which I will talk about is just the extraction of the tangent linear models and the adjoints again from the ensembles. So basically, if you have an ensemble and apply the nonlinear model to the ensemble and look at the output, you can think of the best linear approximation, the best linear map from the initial ensemble to the final ensemble. And this problem, and if you succeed to extract this to extract this linear map, then you can apply it in the variational assimilation algorithm, again without taking the burden of deriving the adjoint and the tangent linear models using either adjoint compilers, automatic differentiation, or just using the differentiation of the code, say by hand, which is done in many ways, because still the automatic differentiation tools are not really do not produce an optimal code in the terms of speed and accuracy. So let's have a look more precisely at what does it mean. For example, do you see my pointer here? Hello.
Yes, I can see.
Yes.
So if you just assume that the model integration in time is just a sequence of applications of the tangent linear models, because basically any large-scale model on small time steps is just represented by some linear maps from the first time, from one time step to another. So, but on the other hand, the data are injected in the data assimilation system at much sparser time grid, I would say. Let's say in atmospheric applications, the data are injected once an hour, or once 3 hours, or 6 hours, depending on the model resolution. So basically, the major ingredient which is needed for data assimilation is the product of these linear maps between the times of the data injection. Just call it M1, M2, and whatsoever. And if we look, for example, at M2, so what we have, so on the input we have the input ensemble, which is represented by a matrix, which is 10 to the 8th elements in the vertical direction, and say 100 elements in this direction. So it's a huge matrix, which is thin, I would say. On the output we have the same matrix, which is represents the ensemble perturbations which come from the output of the nonlinear model, which is applied to the initial ensemble. So we do have an access to all the elements of these matrices. Then the question is, how do we derive a linear map? So the matrix elements of this matrix using the data from these input and output ensembles. So then let's consider a row of this unknown linear map. So since the models since all the models based on the differential equations, then each M1, M2, M3, M4 is basically represented by a very sparse matrix. So the number of non-zero elements in each of these matrices is rather small. So if you, for example, are going to extract the structure of a one-step linear propagator from these ensembles, you are doing quite well, because say if you are having the number of ensemble members around 100, then the row of the differential operator may have even less than 100 of non-zero elements, and then the problem of extracting these non-zero elements in the row of this matrix can be solved exactly. So you simply just assume that M is unknown and make the transposition of these two quantities, like over here. So the E transposed multiplied by M transpose should be equal to E2. I forgot E2, and this system of equations can be solved exactly. But on the other hand, if we are looking at the composition of these matrices, then the number of non-zero elements greatly expands as the number of the so-called primitive propagators increases between the times of data injection, and so the number of non-zero elements may be too large and will be much larger than the number of ensemble members. So in that case, in order to extract a good approximation to the tangent linear model, you have to solve this equation in the least squares sense. And the quality of this solution depends on the type, how do you define the least square problem. So again, on this slide, we see how does this problem then has to be solved. So the real ensemble matrix is not square in this case because the number of unknowns is much larger than the number of ensemble members. So the ensemble size here is around 100, and here it's just maybe an order of magnitude larger. And you solve the problem in terms of the, again, least squares. So you compute the residual of the product of this matrix by this unknown vector, and then minimize the residual with respect to some positive definite matrix M. And the question is, how do you define it? For example, we had a lot of research in terms of just defining this matrix as an identity matrix with some heuristic tuning parameter plus the standard ensemble matrix, which is derived by just taking this perturbations. Basically, this is the background error covariance derived from the ensemble. You may think of it in that way. So, and using these techniques, it was found that you can do a really good job in approximating the tangent linear and adjoint propagators as you integrate simultaneously as you integrate the ensemble forward in time. So you integrate your ensemble, and on the background you can derive a good approximations to the tangent linear and adjoint models. Another line of research in that respect was done a couple of years ago, just how to deal with the non-local operators, because in this propagator, in the model propagator, some of the, this is again, even for one-time step, the model propagator may contain a sequence of local and non-local operators. Non-local operator is shown here like it's letter N, and local operators are usual differential operators which do not have a lot of non-zero elements in the row. But again, in many models we encounter like the non-local operators are usually the solutions of the elliptic equations, or some basically they're defined by iterative solvers of the elliptic operators. So, and since the iterative solvers are usually defined by applying some sparse matrix to the right-hand side, so you can have an access to the non-zero elements of the inverse of N, basically, and employ the sparsity of these matrices L1, L2, and N to -1. And of course, you may know also the approximate knowledge of the sparsity patterns, so they do not stretch far away from the diagonal. And then you can basically use this structure as just when the model goes forward in time, you can memorize the outputs, and you force the model by the ensemble matrix. You memorize the outputs after each step. So applying L1 to the ensemble and memorize the output, then you can also memorize the output of applying N-1 to the ensemble members and L2 and so on. And basically then exploit the property that the inverse of the transposed matrix is just the transpose of the inverse, and then you will have an access to the transposition of the tangent approximation to the tangent linear model. So schematically, this looks like this. So on each time step, you have the output and the input, and the composition, just the model as L2 and L1. And after each application of each operator, you just store the output of this operator in separate arrays, store on the hard drive. And after these arrays do not occupy really much space, because they have the dimension of the ensemble multiplied by the number of degrees of freedom of the model. So, and as you have these guys stored as a sparse matrices, then you have basically then the structure of the tangent linear model, which just you, again, this structure is not stored per se, but it's still just stored as a code of consecutive application of L1, then of the inverse of n-1, n-1 is stored, inverse of n is stored, and then L2. And similarly, you having these matrices, you can do quick transposition, because the matrices are stored in a sparse format, so addresses of the non-zero elements are available. So this is the way how this technique was applied to shallow water equations. Do you see the movie? So this is the solution of the shallow water model, and on the yellow dots show the observations of this solution, which are taken 4 times during the integration time. So these are just the equations. And the shallow water model was discretized with the semi-implicit scheme. So the time difference between the 2 time layers was taken using just the half of the applications of the matrix to the respective states. So this is an implicit term which is moved over here. So the operator had both sparse matrices and the inverse of the sparse matrix, which is not sparse, and has a lot of non-zero elements. But on the other hand, using the technique on the previous slide, it can be efficiently retrieved by, again, storing the intermediate snapshots of the model state. What is more important? Yes?
The shallow water is solved by finite difference or spectral method, or which one?
Finite differences, yes. But okay, it's an implicit scheme, because you see
the time, right? It's
implicit in time. The finite differences, yes. But the major thing is just how to decrease the burden of computing the tangent linear and adjoint operators every time step. So using this scheme, of course, you can increase the time step, but on the other hand, the accuracy of approximation, because of the implicit scheme, will decrease, and so there is a kind of trade-in between the length of the implicit step and the accuracy of the approximation. And what we did, we tested the accuracy of the 4D var scheme in this setting if we extract the tangent linear and the adjoint operators from the ensembles, not every time step, but say every 10 time steps, every 100 time steps, and whatsoever, and see how does it affect the efficiency of the descent of the approximation scheme. So basically, we had the state vector was 30,000 was a toy model and the 27 ensemble members. So this was enough to retrieve all the operators from the ensembles. And these are just the requirements, the wall time requirements for the extraction of tangent linear model normalized by the EWT is the expense of ensemble propagation of one step forward in time. So if we just normalize this by E delta t, then we get just 7.07, and again, on the total, with the extraction of the tangent linear models, you have just only 10% increase of the computational speed, and time interpolation of the tangent linear and adjoint operators was just very, very fast. So because they are saved as sparse matrices, so it's just negligible compared to the computer time and propagating the ensemble forward in time. And so this is just how does this interpolation in time of the tangent linear and adjoint models affect the convergence. So the cost function, this is the reduction of the cost function in several cases. For example, one is just when you extract TLM, tangent linear and adjoint models, every time step. So the error, the final assimilation error is 0.3. So this is basically the exact variational method. With these types of data I've shown, just this is the minimum error you can achieve on that solution with a variational method. But say if you extract the models every 4 or every 8 time steps, still the cost function falls more or less similarly to in a similar manner than the fall of the cost function with the exact solution. And only when you do the interpolation of the tangent linear and adjoint models every 24 time steps, then you have some deterioration of the quality of assimilation. And similar with the gradient, which is shown over here, we see that there was the loss of accuracy just was occurring only when you interpolate the tangent, extract and interpolate tangent linear model in time every 24 time steps, and each time step was in this case 1 hour, so every day. So these experiments show that you can do pretty well if you just do interpolation, the tangent linear and adjoint models in time, and do this extraction not every time step, but in much sparser manner. So, and the summary from this part of the talk, that the ensemble approximations to tangent linear and adjoint operators are feasible, and they're feasible on massively parallel architectures, because you have basically to do this in parallel. You can just extract the lines of the tangent linear and adjoint operators row by row, and so the more processors you have, the more parallelization capabilities you can exploit in extraction of these models. And this technique also allows to bypass the problem of tangent linear model instability in strongly nonlinear regimes. Again, it does not require development of and maintenance of the tangent linear and adjoint models, and this is one of the major advantages in that respect. For example, we have this HiCom model, which contains a lot of if operators, and it's very hard to derive the feasible tangent linear and adjoint model to this one. And right now we are working on this ensemble method of approximating this tangent linear and adjoint operators of the model. And since again the ensembles are less than stencil sizes, so we have to still figure out what approximations are feasible by doing other generalized inversions of these matrices or time interpolation of the exact tangent linear models, as I have shown on the previous slides. And these approaches also can be combined. So we can do the generalized inverse plus do some time interpolation and hopefully get the results which are similar to the application of the tangent linear and adjoint models derived using the either automatic compilers or handwritten differentiation of the codes. And then the problem of the non-locality of the tangent linear matrices like elliptic PDA solvers or standard transformations like the Fourier. The Fourier has a good property that it's just self-adjoint, and so this can be handled with these techniques fairly easily, and that's the major conclusion from this. So these couple of slides I just show you the experiments on the derivation of the adjoint-free sensitivity experiments. So, for example, we have a simple quasi-geostrophic model in a box where in a highly nonlinear regime, when let's say vorticity is measured on this grid of 16 points shown here by stars, and the problem was to compute the sensitivity, say, of the transport between these 2 points, of the mean transport between these 2 points, if the model is integrated for the period of, say, a couple of weeks. So this is a problem, a pure problem of sensitivity, which can be solved if you have the exact adjoint and tangent linear model. So, for example, so the target quantity in this case is the mean transport through this section over 2 weeks. So it's basically a scalar, and control variables are the initial conditions of the model. So M is the nonlinear propagator of the model. M is the nonlinear operator which maps the initial conditions on the final state, and operator Q performs averaging in time and in space of the output. So then if we consider sensitivity of this transport to infinitely small perturbations of the control variables, then we have to just take the derivative of this nonlinear operator in the vicinity of some optimal state with respect to control variables. And here comes just the kind of theoretical, you have to derive the theoretical linearization of M, which is shown here by M, and of Q, shown here by the bold Q letters. So then the sensitivity is just simply the transposition of Q and then the transposition of the tangent linear model. So this would be as a vector of sensitivities, because it's just basically a sensitivity of a scalar quantity to a vector. So this would be kind of a vector showing the sensitivity. But again, how to do this without computing the exact tangent linear and adjoint models for M and Q. This can be done pretty simple, because, for example, you just perturb the initial conditions and look at the respective perturbations of the target quantity, and then compute the correlation between these two guys and apply the inverse of the covariance matrix you have, since you do perturb it and you know how they are perturbed, to this vector, and then you get the estimate of this sensitivity. The problem again is that the number of perturbations, you cannot afford the number of perturbations equal to the dimension of the control variables, to the state. So you have to, you cannot invert this matrix because it has a lot of zero eigenvalues, but you can do the inversion using some pseudo inversion technique, again, just invert it in the least square sense, and obtain reasonable estimates of the sensitivity. over here, just I show you the example of how does the gradient, the sensitivity of this mean transport with respect to variations of the initial conditions look like if you apply the exact tangent linear and adjoint operators and just integrate them backward in time according to this formula. So there's a lot of noise, and this noise associated with the fact that these eddies start interacting and meandering all the way through the time of integration, and in the end you get a mess like that, so which does not show you anything reasonable. But on the other hand, if you consider each map of this type for every perturbation in the ensemble you have, and then average over the perturbations, you get more or less reasonable structure. How this problem is dealt in practical cases. In practical cases, the adjoint model is supplied by artificial diffusion operator, the so-called stabilization of the adjoint model, and the amount of this diffusion can be related to the structure of the model and the time integration you have, basically. And so if you just apply the diffusion operator, then you see, so do not have the exact adjoint model, you see also a more or less realistic sensitivity map, which resembles the sensitivity map obtained by averaging over the ensemble of these noisy patterns. So in that respect, there is a kind of connection between the ensemble methods and the adjoint methods you have in the disposal. But again, to avoid derivation of the adjoint model, you can either do averaging of the ensemble, or if you have the adjoint model at the disposal in this nonlinear regime, you have to introduce our artificial diffusion to approximate the real sensitivity map, like this one. So, and this is just the dependence of the ensemble of the results of the approximating another quantity. I don't remember which one is that. So, but this is just by applying the exact adjoint and tangent linear models, and these are approximations using several iterations using various ensembles. So we see that as the number of ensemble members increase, you are just getting closer to the real sensitivity. So all these exercises just show that, again, if you have massively parallel computers, you may bypass the labor of deriving the adjoint and tangent linear models and just reduce the problems which are connected with their instabilities. So finally, we come to application of the so-called adjoint-free 4D VAR, which was developed maybe a few years ago. I would say like fully developed maybe 5 years ago, and it's it has the foundations closely connected to the 3DF GATT, which Professor Lawless just sketched on the previous lecture. And the basics are, again, just to, if you have the massively parallel architecture, you can perform a kind of blind search for the minimum, as I showed before. And the idea is, again, just to replace the tangent linear model by kind of its approximation. So, for example, first of all, this is the cost function we're going to minimize. So it's just the 4D VAR cost function. This is the summation over time. So on each time we have some difference between the data and the and the model obtained by the application of the observational operator to the model state at this time. So on the other hand, since our system is our 4D system is formulated in the data space, as you remember, the formula again shown by Professor Lovelace. So this is delta x plus some correction, and this correction is resides in the range of B. So it's just this correction is by definition is spent by the eigenmodes of the background area covariance, which can be which may not have the full rank. So this is each gradient is projected on the subspace on the range of the background area covariance matrix. So we just multiply the expression for the gradient derived from this formula by B and get this expression. So we basically have the sum of delta x plus the sum of these members. So again, the problem here again with this tangent linear model, which we do not have at our disposal. So the underlying idea is just similar to the 3D FGAT, that for time integrations, especially in the ocean, the evolution of the state between the data injections may not be very large. So you can assume that the propagator by the tangent linear model is just identity plus some corrections, just associated with the linearized dynamical operator. So it's just can be expanded in this Fourier series, and then you just ignore all these terms and assume that the second term is just B multiplied by the vector of model data with misfits distributed in time. But over here we do not take the sum of these guys, but we take them separately. So we search in multiple directions shown here by the green line, by the green arrows. So this is an ensemble of our search directions, which just hopefully spans, gives a good approximation to the exact gradient on one hand, but on the other hand, it also searches in a bit different directions, which gives him gives this approach some advantage, because the direction to the exact minimum, especially in the multi-dimensional spaces, may be sometimes even orthogonal to the real direction. So, for example, if you have this map of the cost function like an elongated ellipses, and you are far from the point, and you compute the gradient somewhere here, so it will show down, by in reality the direction would be almost perpendicular to the steepest gradient. Anyway, so you have a number of directions in which you do the search, and the problem is now how you update these directions in the iterative process. So the search subspace, again, as it shows that it first the snapshots of the background model trajectory provides you information on the leading modes of M, and the subspace spanned by these guys just gives you information on the model data misfits and information on the leading modes of the background error covariance. So next slide. So the technique we use here is just based on the factorization of the Hessian matrix of the problem, because in our applications we use the inverse of the background error covariance as a kind of inverse of some as the elliptic operator. So the inverse of the background error covariance, the square root of the background error covariance would be a kind of elliptic smoother, which may not be isotropic, but still it would be kind of a good way to regularize the problem. On the other hand, the inverse square root would be represented by a differential operator, which does not occupy a lot of space, a lot of memory, and can be applied to a vector in a simple manner. So then the perturbations for in the data space for every ensemble member can be computed as the model is integrated forward in time as these column vectors. So, and as we see, if we memorize these column vectors, this would provide us with the action of the inverse of the Hessian on the ensemble perturbations. And if we do these guys in memory, then we have an access to the action of the Hessian on the this is the action of the projections of the Hessian matrix on the subspace spanned by the ensemble perturbations, and then on each iteration we just can easily solve a problem of computing the optimal values, optimal coefficients before these ensemble perturbations, using the output of the forward model, which gives us as well not only these vectors but also the perturbations of the cost function. So this is the normal equation, which has the dimension of the number of ensemble members, which is solved just in a fraction of a second. So then computing, as we have our optimal perturbation, so we just make a descent in the cost function, and then compute another set, run the nonlinear model once again, and compute another set of perturbations, and continue the process just to search for the minimal. So the adjoint-free algorithm is just if we put it as a number of instructions. So first we run the model, compute the vector of model states and the model data misfits over here. Then compute the search directions by computing the generalized eigenvalue problem. The search directions are just this matrix P. Generalized eigenvalue problem is computed with respect to the background error covariance matrix, like over here. So these are search directions. Then perturb the model by the columns of S, run the ensemble, and then again compute these values, perturbations of the state, of the cost function, and of the projection of the Hessian on the ensemble space. Then perform H orthogonalization of the search subspace to the previous search subspaces and update the Hessian. So the kind of approximation of the Hessian each time with each iteration, it just gets bigger and bigger. But at a certain level, of course, it may be degenerate and cease giving us any new information on the structure of new information on the observation. So we then, in this case, we just check the restart criterion, see whether the trace of the Hessian did not change much, and then if it does not change much, so we just restart the process, just populate the search subspace with the unexplored modes of the background error covariance, and then go in this cycle back and forth. So this is, unfortunately, the movie will not work. This is a toy experiment. First, we performed with the simple linear model. So we started advection model by using the stochastic advection velocity. Started with the model initial conditions with a Gaussian blob over here, and the final state just on this side is like that. So the Gaussian blob moved from here to here, and in the final state we measured just the final state in these points. We see that's completely stochastic field with very minor signature of the initial conditions over here, and unfortunately the movie is not working. How it will move back to the initial conditions. So anyway, but the final thing is that we using the 4D we managed to get this initial state, to get this initial blob, of course with some error, but pretty small error. And if you apply the adjoint-free 4D, we get almost identical solution from this observed state, the state you see over here, maybe with a little more noise. And the errors, again, the errors in approximating the true solution for the 4D 0.4 and for the adjoint-less 4D at 0.42. So they are almost undistinguishable in that sense. The total amount of CPU for 4D in this case is 1 to 5. But I would say that in realistic cases, it would be much better in favor of adjoint-less 4D, because in a realistic case, the adjoint-free model, in the realistic case, the adjoint model just is much more expensive, and the tangent linear model is much more expensive computationally, maybe 2, 3 to 4 times more expensive than nonlinear model. And so this ratio would be much closer to 1 in a realistic case. And so this example was more or less encouraging, and we moved further to a more realistic case. In the Adriatic Sea, we had this number of observations like CTD stations plus the velocity measurements of the moved arrays. So the total observations was 23,000. The dimension of the state space was 1 million, still much smaller than the number of orbs in the operational systems we have, because it's approximately, I would say, two orders in magnitude larger. So yes.
In this example, the ocean circulation model is ANCOM?
Yes, right. It's ANCOM in Adriatic with tides and with all the bells and whistles. Yes, so this is a realistic model we have. We are running it NRL. So, and I say that still it's 100 times the dimensions of this, approximately 100 times less, but still demonstrate a more or less realistic behavior. And this is the comparison of, we compare the adjoint-free 4D with the 4D which uses the adjoint. So this is the blue line over here. So this is the reduction of the cost function. The blue line is the amount, the performance of the 4D, and this is the adjoint-free 4D. So we see, so one point on this blue curve represents then one outer cycle of the adjoint 4D. So the adjoint 4D uses the incremental approach, and it's formulated in the data space. So one cycle requires I don't remember how many minimization iterations of the purely linear problem, while the adjoint-free 4DVAR, it operates with nonlinear models, then it's in this case it was like 4 to 5 times faster than the adjoint 4DVAR, which operates with the tangent linear and the adjoint of the tangent linear model. So that's why for one outer loop, it used almost 5 times. During the whole time of one outer loop, we could perform 1, 2, 3, 4, 5, or even six iterations of the adjoint-free 4DVAR, and the reduction of the cost function is pretty similar. And this is for the assimilation window of 4 days, which is the typical in our lab. Just as we take 8 days, we still have similar convergence, especially on the first outer loop. And basically, in practice, in regional models, we use only 1 or maybe at most 2 outer loops in assimilating, because and the forecast skills were just pretty similar. So the blue line. So first we integrated the model, assimilated the solution for 4 days, and then just made a free forecast of the starting from the initial conditions after assimilation. And so both lines for the adjoint-free 4DVAR and 4-dimensional are pretty close to each other. And unfortunately, I don't again no movie modes in this situation. This is a comparison of the CPU and wall time. So the wall time, of course, the huge advantage of the adjointless 4DVAR, because it just uses much more CPUs, because it uses this massive parallelization compared to 4DVAR, which is again constrained by this bottleneck I was mentioning at the very beginning of the talk. So it has to perform one search at a time at each iteration, and even in the total CPU time, if you add all the processors, you get more or less reasonable performance of the adjointless 4DVAR. And what's also important, that these were the movies comparing the initial conditions, optimal initial conditions from the adjoint-free 4DVAR and the 4DVAR, the exact 4DVAR. But I would say it's not also exact, because the model has some non-differentiable operators, and I would say that the adjoint model and the tangent linear are just only approximations to the real ones, if they do exist. But the major difference, again, just as you see, the optimal states are different. And this is because the sparsity of observations, so you do not actually capture all. So this is the sparsity of observations. You cannot capture actually in 4 days, for example, the structure of the model in the very south of the sea. But on the other hand, an interesting feature is that the initial conditions for the 4DVAR are much more noisy in the southern part, which is not covered by observations, but the adjoint-free 4DVAR is more or less smooth and does not. And we attribute this to the instability of the tangent linear and the adjoint models. But this question requires further studies. The same technique was applied to the wave model in the Chukchi Sea in Alaska. So we see observations over here. These are 2 satellite tracks. There's also kind of two high frequency radars and 2 wave moorings located over here. And this is a completely different model. It's just the spectral model of the surface waves. It does not have any adjoint, it does not have any tangent linear model yet, but still applying of the adjointless, in this case 5D variational, because each grid point of the model contains a 2D spectrum. So there are 5 dimensions. So physical dimension in the physical space, plus in every grid point you have two spectral components plus time, so it's 5D var. So again, just applying this adjoint-free 4D var algorithm to this model, we get considerable improvements in the significant wave height, which the error is 25 centimeters. In the operational forecast it was 42, and so this is the mean wave period. Again, it's much better improvement in the adjoint-free 4D var. So and this is again the difference in the time mean spectra obtained in the background solution. This is the operational forecast, which is just has the same shape. So it's just because operationally the major impact is defined by the total energy of the surface waves measured from satellites, and total energy is just the integral of the spectrum. And we see just a minor reduction of, it was 4 here, 3 here, and over this maximum was just affected in a not significant way. But the adjoint-free 4D var just made it much more, reduce the overall error and just spread the error and just reduce this huge uncertainty in this part of the spectrum, so that we see some progress and in applicability of this model. Finally, we've got some collaborations with the scientists from Jamstack in Japan. They applied these techniques, adjoint-free 4D variation techniques, to the operational model near the Japanese coast. This is 1/10, I guess, ocean general circulation model run on the Earth simulator, which with peak performance of 1.5 petaflops. And the simulated data, the sea surface height, sea surface temperature, and some CTD profiles. So the major idea of this forecasting system is to monitor the so-called large Kuroshio meander over here, which is a highly nonlinear phenomena actually, and its forecast is a very difficult task. So the model, the simulation scheme was validated against the currently operational scheme. They use so-called multi-scale data assimilation, multi-scale 3D var data assimilation, which applies consecutively a larger scale 3D var plus then just 3D var with background error covariance trying to capture smaller scales. And the adjoint-free 4D var experiments, and both in the 4D var and multi-scale 3D var, there were 4 simulations with 8-day window. Those basically assimilation was performed for 1 month, and then they were followed by the 2-month forecast to have enough time for development of this meander. And we did compare these forecasts for both assimilation systems. One forecast was initialized by multi-scale 3D var and another by adjoint-free 4D var, and this was performed 7 times.
Dr. Yarenchuk,
okay.
We have more 10 minutes. Okay.
Yeah, I'm just coming to the end, and just a few more slides. So, this is just to have a glimpse of what is the outcome. So, for multi-scale 3D var forecasts, the error or the forecast error was significantly larger than the forecast error of these guys. You can see it by the difference in the intensive blue and red colors. I'm a bit colorblind, but so there is basically a large difference between these guys. While on the initial state it was not as visible as well, but in the after 2 months of integration, this error was much in favor of the adjoint list 4D scheme. So another group in Japan was studying the freak waves using, again, the adjoint list 4D scheme. This is in the University of Tokyo, and they used the high-order spectral method for explicit. This is a phase resolve. It's not a spectral model, but it's phase resolving C-surface height model. And the major goal was to find out the dynamical origin of the so-called freak or rouge waves, which may affect vessels in the open sea. And this, the origin of this freak waves comes from the nonlinear interaction of the surface waves. And what they did, they studied surface waves in the Tokyo harbor on a much smaller scale, and they did assimilation of the stereo camera. They used registration of the surface waves using some stereo camera and some different methods of observation of the surface waves at different points. And again, the major conclusion was that adjoint-less 4D assimilation, it revealed an envelope of surface waves oriented obliquely to propagation direction. And this envelope was propagating for tens of wavelengths. So it's just resembling a kind of soliton solution, which was predicted theoretically and is now considered to be the major reason for originating of these freak waves. So in that case, the 4D algorithm provided a kind of tool maybe to study kinematics and dynamics of these waves. So it has some kind of value from the scientific point of view. So, and finally, the summary. The adjoint-free method is I would say, the family of algorithms which use ensemble information to infer the structure of the linearized numerical models and assess their sensitivity to poorly known parameters and perform dynamically constrained data assimilation. And the major feature of these techniques is just to avoid development and maintenance of the linearized model codes and their transposition. And basically, this approach employs the brute force approach of finite differentiation in functional spaces and improved parallelization capabilities of modern computers to replace analytic differentiation of the numerical codes, which are kind of problematic as the models get more complicated. The advantage is much simpler to maintain and update. Numerical models within this approach are used completely black boxes. Sorry, just maybe no. And disadvantage is, of course, a bit higher computational cost, but still, it's how much it's high. It's just need to be explored in the real applications. And so currently this approach has been implemented in a number of models, including ocean general circulation, NCOM, JCOB, surface wave spectral models, both in standard and phase resolving formulations. And the common issue again is just limited affordable ensemble size, which introduces sampling problems and different techniques to tackle them, like localization, special time averaging, etc. And this is again the area of the research right now in the assimilation community. And so this just maybe a few references to the stuff I was talking about on this lecture. And this is all. Thank you for your attention.
Thank you. Max, thank you very much for your very nice presentation. And well, I put in the chat two questions. One, it's about the localization matrix, and another one, it's about the beta parameter. One, and I think that beta parameter, it's slide 12 or something.
Yeah, just regarding the extraction of the tangent linear
Yes,
models.
when you are trying to identify the
this one.
That's it.
Yeah, that one.
Because
yeah,
I think that
just
this parameter is turning by numerical experimentation or something.
Yeah, right, you are. And this is basically the research which was published a few years ago by our meteorological division, and Craig Bishop was just basically, and Sergei Frolov were just at the origin of this research. So and right now they also Craig also wrote a very nice paper on extension of this. It will. I just read the first version, and it was had very good reviews, and it will appear, I guess, in monthly weather review. So you may search for it maybe in the next month. It's just very interesting stuff. And the second question, you say it's about.
It's about the localization matrix in order to do the decomposition. I don't know if the decomposition is single value decomposition, and
this one, right?
You could, yes. And so how many singular values are you considering here?
Yes, we are not doing this research. This is basically the stuff from Leo et al., the paper of Leo et al., maybe 2012, I think. They made it experiments with the WRF model, and as far as I remember, they use like an order of 100 UFs to truncate this localization matrix. So this was the. So they applied the SVD decomposition, just finding the first leading 100 modes of this matrix. So this was their approach.
There is any other question or comments? You are waiting a little bit. If not, well, it's 2:30 a.m. time in Tokyo and Kyoto, Japan.
Exactly.
London, and here in Brazil is 2:30 p.m. And thanks a lot, Max. I very enjoy your presentation today. Very nice.
Thank you, Haroldo, for inviting and everything. Thank you. Just hopefully. And thank you, everybody, for attention.
Thank you very much.
For attention.
Thank you very much.
Goodbye.
Okay, goodbye. You can see